Good afternoon, everyone. Today we will discuss the EMF equation of an alternator. We have certain notations for it. Let phi is equals to flux per pole in Weber, P is equals to number of poles, Ns is the synchronous speed in RPM, F is the frequency of induced EMF in Hertz, then Z is the total number of conductors. ZPH is the total number of conductors per phase connected in series, and ZPH is equals to Z by 3 as we have 3 number of phases R, Y and B. As we know, now we are considering a single conductor placed in a slot. According to Faraday's law of electromagnetic induction, the induced EMF in a conductor is rate of change of flux with respect to time, that is d phi by dt. So now we are considering the one revolution of a conductor. So average EMF per conductor is equals to flux cut in one revolution upon time taken for one revolution. Now this phi, this is the flux produced by one conductor or flux produced per conductor. So the total flux cut in one revolution is phi into number of poles P. Okay, and time taken for one revolution is 60 upon ns seconds. So put these two values in this equation. Therefore, E average per conductor is equals to phi P upon 60 upon ns. So this ns will go upside and it will be like this, phi P ns upon 60. So this is the average EMF per conductor. Okay. By observing this equation, we come to know that the frequency F is equals to Pn upon Pns upon 120. So we can replace this Pns upon 60 by 2F. So E average per conductor is equals to 2F and this remaining 5 volts. So this is the average EMF per conductor. Now this is the average EMF per conductor. Now in a one turn we have two number of conductors. Okay. So average EMF per turn is equals to 2 into EMF per conductor. So what is the EMF per conductor? It is 2F phi multiplied by this 2. So the average EMF per turn we have got 4 F phi volts. Okay. So this is the average EMF per turn. Now this is the value of EMF for one turn. If TPH be the total number of turns per phase connected in series, okay, then the average EMF per phase is equals to, we have to multiply this average EMF per turn into TPH to find out the average EMF per phase. Okay, so EPH is equals to TPH into 4F phi. This is the average value of EMF per phase, TPH into 4F phi. Okay. Now, in a AC circuit, the RMS value of alternating quantity is used for the analysis. Okay, and the form factor is 1.11 in a sinusoidal EMF. So Kf form factor is equals to RMS value upon average value, which is equals to 1.11. So we have to calculate this RMS value. So RMS value of EPH is equals to Kf into average value. So put this value of average value here. Okay. So 1.11 into 4 F phi TPH. So we'll get EPH in RMS is equals to 4.44 F phi TPH. Okay. So this is the equation for the EMF induced in case of alternator. And this TPH is equals to ZPH, that is total number of conductors per phase upon 2. As in one turn we have two numbers of conductor. So this is the EMF equation of alternator. In the next lecture we will discuss the pitch factor or coil span factor and distribution factor. And also we will see the effect of pitch factor and distribution factor on the value of EMF of an alternator. Thank you.